So first of all, I'd like to thank the organisers, of course, for having me here. And just to mention, I'm a PhD student from Tyndall National Institute in Ireland and registered with the Department of Physics in University College Cork. And my supervisor is Ivana Savic, who unfortunately couldn't make it here today. And these are some other of the people within the group. Ronan Murphy, who's actually in Imperial College in London at the moment, and Philip Murphy and Stephen Fahey. So to begin with, I'll give a very brief outline of my talk. So initially, I'm going to talk about the soft mode phase transition in thermoelectric materials. And the idea here is that we want to look at how the soft mode phase transition affects the lattice thermoconductivity and how we can exploit this to push the material closer to the phase transition, reducing the thermoconductivity, potentially increasing the figure of merit. Then I'll move on, and second part of my talk, I'll mention a bit about how we model the lattice thermoconductivity, which from an earlier talk will probably seem a little bit familiar, but yeah. Then for the third part of my talk, I'll move on and show some of the results. And this is on where we take lead telluride and its alloys, and we push them towards the ferroelectric phase transition to reduce the lattice thermoconductivity. Then finally, I'll finish up and talk a bit about the electronic properties and how we model these in first principles. Now, when I'm talking about this, it'll be quite obvious that it's very much a work in progress and quite a bit more needs to be done on that side of things. So to start off with then, I'll focus on the soft mode phase transition in thermoelectric materials and how it impacts the figure of merit. So I'm sure you all already know this anyway, but for the sake of mentioning it, so a thermoelectric converts a temperature gradient to a voltage difference, known as the Seebeck effect, or in the other direction, known as the PlTe effect. And then some applications of this, you already know them anyway, but say waste energy harvesting. If you have, say, a supercomputer and it'll generate waste heat, you can then take this waste heat and use it to generate back some electricity. Second application then might be something like solid state cooling, where you can take a thermoelectric, put it on a device, and then by running an electrical current through it, you apply cooling to the microchip. So the effectiveness of a thermoelectric material is given by the figure of merit, Zt, depends on the electrical conductivity, the square of the Seebeck coefficient, the temperature, and the lattice and electrical thermoconductivities, respectively. Now, the thing about increasing the figure of merit is it can be a little difficult. What ordinarily happens is that as you increase one, you end up decreasing another. So what we want to do is look for ways around this block. Now, the lattice thermoconductivity is somewhat decoupled from other properties. And how we're going to tackle this is we're going to take a look at lead telluride, which has a characteristically low lattice thermoconductivity. We're going to look for the reasons behind this to try to exploit them to reduce the thermoconductivity even further. So to start off with, I'll just mention a few basic properties about the proximity of lead telluride to this lattice instability. Now, it's a group 4,6 material. The lead atom has 2 p valence electrons. The tellurium atom has 4 p valence electrons. These hybridize and are then shared among the octahedral bonds in the material. Ultimately, we see that it forms in the rock salt structure. Now, because of the nature of these bonds, the structure itself is rather weak and prone to distortions. In fact, it's energetically close to a phase transition to the rhombohedral structure. And I have here an example of a rhombohedral material, germanium telluride. Now, what I'm going to do is just compare the differences between rhombohedral and the rock salt material, which I'm sure a lot of you already know anyway, but the main difference is that this central atom here is displaced along the 1-1-1 direction, and the angle here decreases slightly as a result. Now, this is a phenomenon known as Prowl's distortion. So ultimately, the goal here is to look at the proximity of lead telluride to this phase transition, to this ferroelectric phase transition to the rhombohedral structure, and see how this affects the lattice thermoconductivity. So to demonstrate this, I have the phonon band structure here of lead telluride, and because it's near this phase transition to the rhombohedral structure, it has a very soft TIA mode at the gamma point. I've highlighted it here. It's about 1 terahertz. Now, because this mode is so soft, it couples very strongly with acoustic mode phonons. And you can see, say, an indicator of this if you look at the Grunison parameters, where as the frequency gets smaller, the Grunison parameters will get larger. So ultimately, what we see is that this large TO acoustic interaction in lead telluride results in very low phonon lifetimes, which give rise to its characteristically low lattice thermal conductivity. But the question, so that's all well and good. The question is, what can we do with that? So the idea I want to talk about here is we want to take lead telluride and push it towards the phase transition. This will soften that TO mode at the gamma point, increasing that TO acoustic interaction, reducing the phonon lifetimes, and reducing the lattice thermal conductivity. And then hopefully we get quite a nice boost to the thermoelectric figure of merit. But as I mentioned earlier, in the thermoelectric figure of merit, we have some other properties that we have to take into consideration as well, such as the electronic properties. Now, this is maybe a little hand-wavy, but I have here the electronic band structure of lead telluride. If you just focus here on the valence band maximum and conduction band minimum. Now, it turns out if we look at scattering of electrons by a TO mode phonon at the gamma point, from these 2 points, it's forbidden by symmetry. So this gives us a little bit of a hint that as we begin to push lead telluride towards the phase transition, softening that TO mode, the electronic properties may not be that negatively impacted. However, that's strictly only at the L point. Away from the L point, we would expect there to be some electron-phonon interaction. And just to mention that a bit briefly, so you can see the thermoelectric figure of merit again, where these in green are the electronic properties. And so as I mentioned, away from this L point, there will be some moderate electron-phonon interaction. But as we get nearer the phase transition, we will have very strong phonon-phonon interaction. So the hope here is that as we get near the phase transition, electronic properties will not be that negatively affected, but even if they are, the gains we make to the reduction in the lattice thermal conductivity will far outweigh it, potentially greatly enhancing the figure of merit. And just to briefly mention as well, this isn't, say, specific to lead telluride. This strategy could work on really any material with a similar soft mode phase transition. So now I just want to talk a bit about this. So that was all a little bit hand-wavy, but if we take a look in the literature for an example of a high ZT material near phase transition, PUB's tin selenide. Now, it's a group 4-6 material like lead telluride, and it undergoes the phase transition as a function of temperature. So here is the high temperature phase, it's orthorhombic, and you can view this sort of as a distortion of the rock salt phase. Now, as you lower the temperature, there'll be a phase transition at about 800 Kelvin, and the structure it'll transition to a lower symmetry structure. You can see what that looks like here. So now, from this paper, if we take a look at the thermal conductivity of tin selenide, you see that it's extraordinarily low. It's about 3 times lower than that of lead telluride. And interestingly, if we take a look around the phase transition, we can see that there's an ever so slight kink in the thermal conductivity near that point. So now again, let's take a look at the electronic properties of tin selenide and see how they're affected. So we have here the power factor of tin selenide, or the power factor, for anyone who doesn't know, is just the electrical conductivity times the Seebeck coefficient squared. And looking at this, in terms of thermoelectric, these values maybe aren't anything to write home about, but if we look near again that phase transition temperature, it actually turns out that these values peak. So I guess I'm not going to claim that the phase transition is necessarily enhancing these properties, but it does show that as tin selenide undergoes the phase transition, these aren't negatively impacted. So, and this results, coupled with the low thermal conductivity you saw on the previous slide, give rise to tin selenide's very high ZT of about 2.6 at 900 Kelvin. So this is just quite a nice demonstration of the fact that if we take lead telluride, push it towards the phase transition, reduce the lattice thermal conductivity, we could greatly enhance ZT, and who knows. Okay, so now moving on, I want to talk a bit about the second part, which is how we model the lattice thermal conductivity from first principles. So to start off with, we go to the Boltzmann transport equation in the relaxation time approximation, where omega are the phonon frequencies, v are the group velocities, and tau are the phonon lifetimes. Now, in order to calculate these phonon lifetimes, we model them first of all due to 3 phonon interactions, neglecting higher order interactions. This is where, say, 1 phonon scatters to give 2 new phonons, or 2 phonons combine to give 1 new phonon. In the second case, we calculate phonon lifetimes due to mass disorder. Now, in this case, we take an average potential of the system and then add a perturbation on top of this to get effective phonon lifetimes using Fermi's golden rule. We then add these lifetimes due to mass disorder back into our lifetimes due to 3 phonon interactions and get the total phonon lifetimes for our system. Now, I will just mention as well that because of the way we do this, we do slightly overestimate the phonon lifetimes, so the resulting thermoconductivities will be a bit above where they would be in reality. But anyway, we then use DFT to calculate these quantities, and to just mention that. So we use a finite difference supercell approach. This will probably seem a little bit familiar, but we use the phonon 3-byte code to generate our supercells and to then generate atomic displacements within them. Now, we then pass these displacements to Abinit, and using DFT, we calculate the interatomic force constants. Now, from the first order derivative of the forces with respect to atomic displacement, or you can say imagine displacing 1 atom and calculating the forces on all the other atoms due to this displacement, you get the phonon frequencies omega and the group velocities v. And from the second order derivative of the forces with respect to atomic displacement, you can get the anharmonic phonon lifetimes tau, and then plugging it back into the formula here, we can get the lattice thermoconductivity. So now the question is, how does this theory compare to the experiment? So I have here the phonon band structure again of lead telluride. Our curve is in black, and these blue dots are inelastic neutron scattering data captured at 300 Kelvin. And all we can see is we do get very good agreement between the experiment and our theory, with one very important caveat, and that is that since we're using DFT, our calculations are at 0 Kelvin, so we don't capture the temperature dependence of that TO mode phonon at the gamma point. And in reality, as you increase the temperature, that TO mode will also tend to increase upwards, which isn't captured. And that does play a slight role in the thermoconductivity. Here's a function of temperature. Our calculated curve is in black, and we have 2 sets of experimental data in blue and red. For low temperatures, say 100 to 300 Kelvin, our results are about maybe 20% higher than the experiment. Now, from about 300 Kelvin upward, the results appear to be very good and agree very well, but you will notice that the temperature dependence is slightly different. So say the calculated curve goes down like this, but the experimental data points cross over. Now, this is because of what I mentioned previously about that increase of the TO mode frequency, which has a tendency to increase the thermoconductivity as you get to higher and higher temperatures. So that is something that unfortunately isn't captured by our theory, but nevertheless, as we go on, we will be able to look at trends in changes in the thermoconductivity and see what happens as we get nearer the phase transition. So to move on then and start talking a bit about the results. So I'm going to focus on, essentially pushing lead telluride towards the ferroelectric phase transition, showing you 3 of our approaches to do this to reduce the lattice thermoconductivity. So this section will be subdivided into 3 different sections here. The first one is to take lead telluride, apply biaxial tensile 001 strain to it. What we want to do in that case is apply enough to push it towards the verge of the phase transition, but keep it in the tetragonal phase. Similarly, for the second strategy, we ally lead telluride with another rock solid material, lead selenide, and again, we apply biaxial tensile 001 strain to this. And then finally, I'll finish up this section and talk a bit about alloying lead telluride with the rhombohedral material, germanium telluride. Now, in this case, it's useful because you remove the need for strain in the previous 2 examples, And by simply increasing the germanium content, you push the ally closer to the phase transition. And I'll get back to that later. So first off, I'll just talk a bit about applying biaxial tensile 001 strain to lead telluride. So to start off with, again, I have the phonon band structure of lead telluride. I've highlighted, again, the TMO at the gamma point with this black circle. It's at a frequency of about 1 terahertz. So, as mentioned, what we want to do here is apply enough strain to lead telluride to push it towards the verge of the phase transition, but keep it in the tetragonal phase. And maybe an example of how you might do this experimentally might be to take lead telluride and grow it on a substrate with a larger lattice constant. So applying 1.15% of strain, we get this red phonon band structure here. Now you can see there are maybe a few differences away from the zone center, but the major difference occurs at the gamma point. Or you can see in the case of lead telluride, this TMO has dropped from 1 terahertz down to about 0.1 terahertz in the strain lead telluride case. Now I will just briefly mention that 1.15% of strain is rather a lot of strain to apply in this case, but the goal here is maybe to look at this more as a thought experiment in a way, and to see what happens if we push it to the verge of the phase transition. So getting back to that, so we've softened the TO mode considerably at the gamma point. We've increased that TO acoustic interaction. If we take a look at what happens to the phonon lifetimes, have here lifetimes due to 3 phonon interactions, and lead telluride again is in black, and strain lead telluride is in red. And we see we get quite a substantial reduction to the phonon lifetimes due to this increased TO acoustic interaction. And what's also quite interesting here is if we take a look in the top right, we see a little inset here of the averaged phonon lifetimes as a function of frequency. And the thing here is that this reduction in phonon lifetimes is maintained across the frequency spectrum, particularly helping to scatter those low frequency phonons. Now, you'll probably recognize this picture. It's already been shown once already, but this is, say, another approach to achieve the same effect. So in this case, in order to scatter phonons across the frequency spectrum, you say introduce dopants on the atomic scale to scatter high frequency phonons, nanoparticles on the nanoscale to help scatter mid-frequency phonons, and then you introduce grain boundaries to target low-frequency phonons. And what our approach demonstrates is that by pushing lead telluride to the verge of the phase transition, you can achieve the same effect as this approach and scatter phonon lifetimes, particularly those low-frequency phonon lifetimes. So moving back to our results. So this is again the thermoconductivity, and lead telluride is in black, and strain lead telluride is in red. And we see we get quite a nice reduction of about 1.5 by about a factor of 1.5 in this case. So again, I'll sound a bit like a broken record, but we've pushed lead telluride to the verge of the phase transition, increased that TO acoustic interaction, leading to this reduction in the thermoconductivity. So quite nicely demonstrates at least the principle of it. But now, just before I move on, I want to talk a bit more about the strain case. So here I have the thermoconductivity as a function of strain. Positive strain is what I've been showing you so far, this tensile 001 strain, and negative strain is compressive strain. And I have here a little inset on the top right of the TO mode frequency at the gamma point. And what you can see here, let's say by pushing lead telluride away from the phase transition, you'll increase the TO mode frequency and get a corresponding increase in the thermoconductivity. And then, again, as I've just been saying, by softening that TO mode frequency at the gamma point, you reduce the lattice thermoconductivity. So it just further reinforces the point I've said a few times now, that you can push lead telluride away from or closer to the phase transition, and by controlling that TO mode frequency at the gamma point, you can alter the thermoconductivity as you like. So now I'll move on and talk a bit about the second approach, which is to take lead telluride and ally it with a rock solid material, lead selenide, and then apply biaxial tensile 001 strain to this. So just to mention, we use the virtual crystal approximation to model our alloys. And here I have the phonon band structure of lead telluride in black, and this lead telluride, lead selenide alloy in red, about 50-50 mixture. And looking at the phonon band structures, we see there are a few differences, but this is largely due to the fact that the alloys and lead telluride have a different mass, and particularly if we look at the frequency of the TO mode at the gamma point, you see that it's more or less the same. So by alloying, we haven't pushed it towards the phase transition, but we have introduced mass disorder. So calculating the thermoconductivity of this alloy, we get this green curve here, where again we get a reduction by about a factor of 1.5 due to the effects of mass disorder. Now in this case, coincidentally, it happens to line up very well with the strain lead telluride case, but there's no reason it should. But now I want to talk a bit about how we take this alloy and, as we did for lead telluride, apply tensile 001 strain again. So I have here the phonon band structures of this is this lead telluride, lead selenide alloy unstrained in black and then strained in red. And again, it's a pretty similar story. We see that away from the zone center, there's a little bit of difference in the phonon frequencies, but they're largely similar. But the main difference, again, occurs right at the gamma point, where one of the TO mode frequencies has dropped from about maybe 1.2 terahertz down to about 0.1. And just to mention again, in this case, we've applied 1.32% of strain. Again, similarly, like for lead telluride, it's enough to push it towards the verge of the phase transition, but keep it in the tetragonal phase. And again, with that caveat that 1.32% of strain is rather a lot, but again, this should probably be thought of more as a thought experiment of what we do, of what happens when we push it towards the verge of the phase transition. And that TO mode again, soft. And now to look at the phonon lifetimes. So I have here the anormonic phonon lifetimes. Again, black is unstrained and red is strained. And again, you see the same story developing, where we see a substantial reduction in the phonon lifetimes due to that strain. And again, we see this reduction in phonon lifetimes is maintained across the frequency spectrum. Now, if we take a look, now these are lifetimes due to mass disorder in black, and then due to anormonic processes in red. And we see that the introduction of mass disorder in the alloy really helps to scatter those, say, high-frequency phonons above 2 terahertz, where the lower frequency lifetimes below 2 terahertz are really scattered by the anormonic processes. So by increasing the proximity of this alloy to the phase transition, you can really help to target the scattering of those low-frequency phonons. And now what happens to the thermoconductivity? You get this blue curve here, where we see it's reduced by about a factor of 2.4 compared to that of lead telluride. Again, by combining these effects of increased proximity to the phase transition to increase that TO acoustic interaction and the effects of mass disorder from the alloy. So now I want to move on and talk a bit about the third approach, which was to take lead telluride and alloy it with a rhombohedral material, germanium telluride. Now, in this case, you remove the need for strain, and by simply increasing the germanium content, we can push the alloy to the verge of the phase transition. So just to demonstrate this, I have a little mock-up here of, say, the TO mode frequency against the structure. You can see in Roxel phase, you have lead telluride, and then the rhombohedral phase, you have germanium telluride. And as you vary the alloy composition, you can imagine it gets closer to the phase transition, the TO mode becomes softer, and the phase transition occurs here. Now this expands a bit on what I've previously been talking about, because beforehand, in the case of lead telluride and lead selenide alloy, we push it towards the verge of the phase transition, but we kept things in the tetragonal phase. Now in this case, we can actually look at what happens to the thermoconductivity as we undergo that phase transition and see how the thermoconductivity behaves in both the rock salt and the rhombohedral phases of the alloy. So just briefly, I want to take a moment to look at, say, what happens in the real world. And here I have the phase diagram of lead germanium telluride. Now, as it turns out, in reality, these alloys undergo the phase transition as a function of temperature and alloy composition. So, say for example, if you take a composition, you'll see that as you increase the temperature, it'll go from the rhombohedral to the cubic phases as a function of that. Now, as I've mentioned a few times already, our temperatures are DFT, they're done at 0 Kelvin. Our interatomic force constants are temperature independent. So unfortunately, we're not going to capture that phase transition as a function of temperature. But we will capture it as a function of alloy composition. So to demonstrate that, I have here again morphonon band structures. Lead telluride is in black. And in green, I have this lead 51 germanium 49 telluride alloy. Now I've chosen this specific composition, again, as is the case for strain lead telluride, to push the alloy to the verge of the phase transition, but keep it in the rock salt phase. And again, you can see away from the zone center, there are a few differences in the phonon dispersions, largely due to the different mass of the lead telluride and the alloy. But the main difference occurs right here at the gamma point, where you can see that the TE mode frequency, again as before, say has dropped from about 1 terahertz down to about 0.1 terahertz in the alloy. So now if we consider this lead 51 germanium 49% alloy and take a look again at our phase diagram, you see it going up here, the phase transition for this particular alloy in reality occurs at about a temperature of 450 Kelvin. So this is just to point out the fact that we would expect our model then to be most representative of, say, the real world in and around this temperature here. So when I go on to show you the thermoconductivity results for these lead germanium telluride alloys, I will be quoting them at 450 Kelvin. So then just to show you as well what happens here. So this is the TE mode frequency of these lead germanium telluride alloys as a function of composition. And as you can probably imagine, and as you say, start from lead telluride here at 0, you increase the germanium content, you soften that TE mode until you get to the verge of the phase transition here at about x is equal to 0.5. And similarly, if you say start from germanium telluride, you increase the lead content, soften that TE mode, and again you get to the verge of the phase transition, hitting 0 here. So this just shows that although our interatomic force constants are temperature independent, we do still capture this phase transition as a function of alloy composition. And by simply varying that, we can control the proximity of these lead germanium telluride alloys to the phase transition. And now I want to talk about what happens to the phonon lifetimes right on the verge of that. So I have here the anemonic phonon lifetimes only. I'm excluding mass disorder for the moment. And I'll just take a moment to focus on the left-hand side of the slide. This is the rock salt phase. Lead telluride is in black. And this lead 51 germanium 49, again, which was chosen to be on the verge of the phase transition in the rock salt phase. And here we see we get quite a nice reduction in phonon lifetimes at lower frequencies. Now it might be a bit difficult to see there. So again, if you look at this inset in the top right, which shows the averaged phonon lifetimes as a function of frequency, you can see there's quite a nice reduction there at lower frequencies, where at higher frequencies, not so much is happening. Now if I take a look at the rhombohedral phase here, again the anemonic phonon lifetimes, germanium telluride in black, and this alloy composition on the verge of the phase transition in the rhombohedral phase. And we see, in this case, we have quite a nice reduction in the phonon lifetimes. And again, to stress in this case, we see that the lifetimes are reduced across the frequency spectrum by quite a large amount. But what is most important in this slide is the fact that these anemonic phonon lifetimes are minimized at the phase transition. And just to focus a bit more on that particular point, So I plot, here's a plot of the phonon lifetimes of the rock salt alloy on the verge of the phase transition in black, and then red, the rhombohedral alloy on the verge of the phase transition. And you see that they're actually remarkably similar. It's very difficult to even tell them apart. And again, if you look here at the average phonon lifetimes, it's a similar story. So this just points out two things. The first one being that our phonon lifetimes are minimized at the phase transition, but also in these lead germanium telluride alloys, they undergo a second order phase transition. So properties such as the phonon lifetimes, lattice parameters should vary continuously. So now moving on, I've talked about it quite enough. I want to show what happens to the thermoconductivity as a function of alloy composition. And again, just to remind you, I'm showing here the results at 450 Kelvin, because this is where we expect our model to be most representative of the real world. So this black curve here is the thermoconductivity due to those three phonon interactions only. And the inset here on the top left, I have that TU mode frequency at the gamma point, just as a point of reference. So I'm going to make the bold claim that the anharmonic thermoconductivity is minimized at the phase transition here. And you're probably looking at that graph and thinking that while it is a minimum, it's not exactly, say compared to here, it's not that much of a minimum. So I'm going to spend a few slides talking about why that's the case. And to talk about this, bring back the formula for the lattice thermoconductivity, and just to specifically draw your attention to the square of the group velocities and the tau, which are maybe the two main contributions to the lattice thermoconductivity. So if we just focus on the rock salt side of the phase transition for the moment, 0 is lead telluride, and if we just imagine increasing the germanium content, we get nearer the phase transition, as I've been discussing, and our phonon lifetimes reduced, as I showed you previously. But as we get nearer the phase transition, the germanium content is increasing, so our masses are getting lighter, so group velocities are actually increasing. So this results in the group velocities competing with the reduction in the phonon lifetimes, leading to this very modest reduction in the thermoconductivity. Now if we take a look at what happens to the rhombohedral phase, we don't have this as such. So if we start in germanium telluride at 1, we increase the lead content, pushing it closer to the phase transition. Now in this case, as I've shown you again, the phonon lifetimes reduce as we do this, but because our mass is getting heavier, our group velocities are decreasing as well as the phonon lifetimes, leading to maybe about a factor of 2 reduction in the thermoconductivity comparing germanium telluride to, say, this point at the phase transition. So we see that this mass difference in the alloy is definitely impacting how well we can see this minimum value here at the phase transition. So if we do a little thought experiment and imagine our alloy as, say, each composition is having the same mass, we get this red curve here. I will just mention here in the top left, this black curve is the TU mode frequency at the gamma point where each alloy composition has its own mass. And then red is where I've renormalized these masses to be the same. And you see that while there may be a slight difference here and here, but more or less they are the same curves. So it's showing that as we do get nearer the phase transition, that it is just that and not, say, the mass difference that is reducing our TU mode frequency. And then finally, looking at the thermoconductivity, you see this red curve here, and the group velocities are no longer competing with our phonon lifetimes, so we get quite a nice reduction, starting from lead telluride, going towards the phase transition, and similarly, on the rhombohedral phase, getting a nice reduction, though it's perhaps not as obvious now because we've removed the reducing group velocities that have assisted the reduction in this case. But it does highlight the fact that our anharmonic thermoconductivity is minimized at the phase transition. So now I just want to take a bit of a moment just to go back, and this is the slide I showed you previously. Now what we want to do is take into account mass disorder. So in doing that, we get this blue curve here, which is the thermoconductivity due to mass disorder and anormonic processes. And we see that we get quite a substantial reduction to the thermoconductivity, again combining these two effects of the softening of the TO mode, increasing the TO acoustic interaction, and the effects of mass disorder. Now there are a couple of things happening here just to draw your attention to. So if we take a look here at the phase transition along this green line, see the minimum value here. However, we see that the minimum value, when we take mass disorder into account, happens about here. Now, if we take the formula for mass disorder and differentiate it, we find that it's greatest for about a composition of about x is equal to 0.4. So what's happening here is the phase transition wants to minimize thermoconductivity here. Say mass disorder is acting to minimize thermoconductivity at about here, and these, while they compete with each other, they eventually compromise, and we see this minimum thermoconductivity at about here, 0.6. So just to mention as well, if we say take this minimum value and compare it to lead telluride, we see that the thermoconductivity is reduced by about a factor of 3. And then comparing it to germanium telluride, we see that it's reduced by about a factor of 7. So I just want to take this moment to say before I move on to the final part of the talk and just briefly summarize a few of the main things I've shown you from this section. So you saw for the case of that lead telluride and lead telluride alloy with lead selenide that by driving them towards the verge of this ferroelectric phase transition, we can substantially reduce the lattice thermoconductivity. And just as I showed you there, that in lead germanium telluride, the anormonic contribution to thermoconductivity is minimized at the phase transition. And once you take into account mass disorder, that minimum actually shifts into the rhombohedral phase. But again, because you're combining the effects of mass disorder with increased proximity to the phase transition, you get quite a substantial reduction to that. Okay, so now I'll move on and talk a bit about the final part, which is modeling electronic properties from first principles. And this will be a slight change of gear, and it will be fairly obvious when I'm talking about it that this is still very much a work in progress. But nevertheless, so to start with, we return to the Boltzmann transport equation in the relaxation time approximation. And this is the formula for the electrical conductivity, where epsilon are the electronic energies, v are the group velocities, and tau are the electronic lifetimes. Now we model these electronic lifetimes due to electron-phonon interaction, and we use DFT to calculate these quantities. So to model electron-phonon interaction, what we do is we subdivide the different processes into whether they occur by a large wave vector phonon or a short wave vector phonon. So I'll just talk a bit about the intervalley phonon scattering case first, which is via a large wave vector phonon. Now, this is the electronic band structure of lead telluride. It has 4 equivalent L valleys, and you can imagine, say, an electron scattering from one L valley to another L valley via an X-point phonon. Now, as luck would have it, in the case of lead telluride, this particular scattering mechanism is also forbidden by symmetry. But if we say take the case of germanium, it's not. So we do have to take that into account there. So the second type of interaction we take into account is intra-valley scattering. And this is where you can imagine a very short wave vector phonon scattering an electron from one point in L valley to another point within that same L valley. Now, I'll just very briefly give you a sense of what it takes to calculate, say, this quantity in the case of intra-valley acoustic scattering. So to do this, you need to find a splitting in the conduction band energy due to the presence of a phonon. So what you do is you construct a supercell, say, like this little mock-up here. You calculate the electronic band structure, and then you measure from L along a specific direction out to the zone edge, and you get this here. Now, what we do is we then freeze in a phonon. So you can imagine taking your atoms and displacing them according to the amplitude of this phonon. And then you recalculate the electronic band structure, and at the zone edge of the supercell, you get the splitting in the electronic states, and you then take this splitting and you plug it back into some formulas which I won't dwell too much on, and you can calculate your scattering rates due to intravalley acoustic scattering. So in the case of germanium, just to show you what that looks like, so I have a calculated curve in green here, and some experimental data points in green, and for the case of germanium, we do get very good agreement, and as it turns out, the dominant mechanism here is this intravalley acoustic scattering. Now, repeating this for lead telluride, we run into a few different issues. So lead telluride has a very narrow band gap at the L point, about say 0.3 electron volts. So if we take the electronic band structure here and include spin-orbit coupling, we run into a problem. And you can see here that the valence band and the conduction band are very close to each other, and there's mixing of the states and an inverted band gap. Just to talk briefly about that last point. So this is a DFT calculation. So DFT, as it turns out, is actually underestimating our band gap. So this leads to a situation where we have a crossover of the conduction and the valence bands here. And what happens then is a slight gap does open up, but because of the crossover and the negative band gap, the character of the states, say here and here, is different. So if you try to calculate the effective masses from this band structure here, they're going to be very poor. So to get around that, we have to go to something a bit beyond this basic approximation and start looking into something like a hybrid functional. In this case, I've just chosen HSE03. So then, just to focus in here on the band gap, we see that the HSE, we see the curvature of the bands looks a lot more reasonable in this hybrid functional compared to the case of LDA. And measuring the value for the band gap, we see LDA had about minus 0.32, but the hybrid functional captures a very good value of about 0.24 compared to the experiment at 4 Kelvin of about 0.19 eV. So now just to show you some of the values for the effective masses and just show you how poor they can be for LDA. So taking this conduction band mass for LDA, it gives a value of about 5.29 compared to, say, the experimental value of 0.21. And again, just illustrating this a bit more, using the hybrid functional, we capture a value of about 0.246 in much, much better agreement with the experiment than the LDA case. So now just going back a little bit, I want to talk about what happens to the electronic band structure if you, say, neglect spin-orbit coupling. And in this case, we do see that we do capture a positive band gap. We do capture a positive band gap, but the splitting between the first and second conduction band energies is inaccurate, and there's a little bit of mixing here. So deformation potentials here are what we plug back in to calculate our intravalley acoustic scattering rates, and these are going to be inaccurate in this case. So just to show you what happens to the electronic band structure, if again black is this hybrid functional, blue is LDA, and you can see the inaccurate splitting of the conduction band energies. So this was really just to get across the point that in the case of lead telluride, we do need to go to something beyond, say, LDA and have to use a hybrid functional to properly capture these electronic properties. So now getting back to this, I just want to talk a bit about another type of electron-phonon interaction, which is polar optical phonon coupling. And just to give you a little bit of a sense for what we do here, so in our case, we use a model to describe it. Now, it's not this particular model here. This is, say, a very simple model from the 70s in a simple isotropic parabolic band case, where V is the carrier velocity, and epsilon infinity and 0 are the high frequency and static dielectric constants. And by plugging these into the formula, you get your scattering rate for polar optical phonon coupling. Now, you also might think that you could calculate this from electron-phonon matrix elements, but previously these were captured inaccurately by density functional perturbation theory. And just to mention, this group here has worked on improving the accuracy of these electron-phonon matrix elements to capture Froelich interaction properly. But I won't dwell too much on that. I'll move on and show our mobility for lead telluride. And again, we see that we get about value that's about 2 to 3 times higher than the experiment. And so far, from what we can tell, polar optical phonon scattering is the dominant mechanism. But it is clear we need to move to something beyond DFT to be able to properly capture these electronic properties. Okay, so now to finish up. So when we look at the literature, we can see that these materials near a phase transition look to be quite promising candidates for ultra-low lattice thermal conductivities and hopefully potentially high ZT. And this is a little familiar, but I show that by pushing the telluride towards the ferroelectric phase transition, you can significantly reduce the lattice thermal conductivity, and that in particular, in the germanium telluride, the anormonic contribution to thermal conductivity is minimized at the phase transition. And as you saw from that last section, we still have quite a lot of work to do in terms of capturing the electronic transfer properties of telluride and materials near the phase transition. And thank you for your attention.